Notice all the numbers on this slide. There are no decimal points. Done on purpose. Please note, for anybody who's going to be upset if it doesn't turn out to be 10.00, please look at the bottom right-hand corner. These are very rough estimates. Okay? This is utterly for illustration purposes. Now, of course, there are 10,000 engineers at NVIDIA, and they're working really, really hard at every single level of this, from process to circuits to architecture to design to all the middleware and the software and the system, the interconnects, all of that to make this possible. I condensed it all into one slide. All right, so I'm being unfair to so many people that I can't even, but I'm hoping that it could explain why I'm so excited about Pascal. First of all, the forward path. The forward path is the first path or the inference path. This is forward. You do convolution layers, and then you do the fully connected layers, and then it generates a result. If it's a training run, then you compare that result with the right answer, and you compute the delta, the error term, and you backpropagate it, and you do stochastic gradient descent, and then you try it again. Okay? So the forward path, and we're talking about learning right now, the forward path benefits 4x from the convolution layers, right? 4x, 2x from just the architecture itself, and then 2x from the mixed precision in FP16, so that's 4x. And then when it hits the fully connected layers, it's 3 times the bandwidth, but we also have FP16 now, which doubles the bandwidth. So it gives you 6x. And then now when you're working backwards, you get the back propagation now, and it's 6x because of the bandwidth, and then 4x because of the convolution layer. Well, you know, it's kind of hard to say exactly where, how many convolution layers and as opposed to how many fully connected layers and so on and so forth. And so I just kind of roughly said 5x. It's 5x faster as a result of several things. Mixed precision, well, the Pascal architecture itself, mixed precision, and the benefits of 3D memory that is not just wide, but also very, very large, so that we could keep a large network in one compute node. But it's more than that. One of the things that most people are they're just out of their minds excited about is NVLink. I'm out of my mind excited about it. The reason for that is this. We just simply get enough performance out of the single largest GPU on the planet. Now, just to give you a frame of reference, the box that I just showed is dev kit. The Digits dev kit has 4 GPUs, each one's with 7 teraflops, 28 teraflops in 1,300 watts. 28 teraflops in 1,000 watts, 1,300. If you compare that to a supercomputer, in the year 2000, it takes 1 million watts to deliver 1 teraflops. It's 28 times faster than the supercomputer, the fastest supercomputer in the year 2000, and it's 1/10 the power. Is it 1/10? No, 1,000 times less power. 28 times more computation, 1,000 less times power. Okay? So incredible advancements. Supercomputer next to your box. Well, what we like to do, of course, we could use way more computational capability than that. And NVLink allows you to now scale more GPUs. And the reason for that is because if you're going to split the work across multiple GPUs every so often, you're going to have to update the weights across multiple GPUs. And that is interconnect limited. We now have NVLink, which is 5 times the performance of PCI Express. And if the performance of the computation is 5 times, it says that we can take Digits, which has 4 GPUs today, and convert it and upgrade it to 4 Pascals. However, because we also have mixed mode, mixed precision, we can double the interconnect bandwidth, and as a result, instead of 4 GPUs, the next Digits dev box will likely have 8 GPUs. 8 GPUs. 8 GPUs. And so what that allows people to do, literally, is to train 10 times faster. The training problem is one of the most challenging computational problems today. It is one of the most important computational problems today, and now we could do it 10 times faster.